We'll start the recording. Happy Groundhog's Day. I know, this is a thing. It's a very silly tradition in the U.S. where there is a rodent called a groundhog in Pennsylvania, Puxatawney, does that sound right? Pennsylvania? And if he comes out of his hidey hole and sees his shadow and goes back in, then that is a prediction of 6 more weeks of winter. If he comes out of his hidey hole and doesn't go back in, then we'll have an earlier spring. I have no idea why this started or why it is still a thing, but it is a thing. And I watched the video this morning. Spoiler alert, he went back in his hidey hole and we have 6 more weeks of winter, which in Iowa is the best case scenario, I think. Like mid-March, if winter were over, like really over by mid-March, I would be very pleased with this, but I'm not going to be that optimistic. So happy Groundhog's Day to everyone. Let's see. You don't have anything due next Monday for this class, but you do have a homework that you can be working on. If you run into any technical glitches while you trying to do the homework, either in downloading your data set, pulling up the page, please let me know. They should all be fixed. We had to transfer everything over into a secure HTTP thing over winter because we were running into these like security issues where it wouldn't let people access the system. That should all be fixed. So if you encounter any technical difficulties, please let me know. Word to the wise, if you haven't had a chance to do my types of homeworks, start early. They are not the kind of thing that you can do at the last minute unless you absolutely know what you're doing and need no help whatsoever. Otherwise, I would recommend starting in advance. That way, if you get stuck, you'll have time to ask me for help, to ask your TA Vladimir for help over email, office hours, or during class. So you do have a ways until it's due, but I just want to put that out there that these can take a while. How long it takes you is directly proportionate to how comfortable you feel with the material. So I'm assuming there's no homework questions yet. I haven't gotten any over email at least. Okay. Yes, you do?
I do.
You
Yeah,
do? Okay. Our first one.
Yeah.
Exciting.
Yeah, I guess like I got some of the values like correct, but then some of them like, so I guess I got an estimate for residual variance and it's telling me that it's wrong, but then I got an estimate for fixed intercept correct. So I'm just kind of struggling with figuring out how to identify what I did wrong there.
So if the residual variance is wrong, I would make sure that you've entered it to 2 significant digits after the decimal, because that's the level of precision it's checking to.
Okay.
If you're using R, then sometimes it doesn't print enough digits.
Yeah.
is the problem.
Yeah.
So up in the very top of the R syntax file, I have a global option as to how many significant digits I want it to print.
Okay.
You can increase that.
Okay.
If that doesn't work universally. Another way is that if you can locate the object where that information is stored over on the right-hand side, you might be able to see a number with greater precision than that.
Gotcha.
If those 2 don't work, send me an email with a screenshot of what you're trying to do, and I can make sure that there's not some other reason for the problem.
Okay. All right. Thank you.
Sure. One other caveat about the homework as a data analysis, you will see that in the paragraph completion results sections, your numbers show up. They are populated from whatever your last answer was. So if you haven't answered the question, the numbers will all be 0. If you have the question wrong, it will pull whatever the last entered value was, even if it's wrong. So they populate down. It's not a guarantee that it's right in one place or wrong the other. The numbers are all checked up above, and you'll know it's right if it turns green. So happy to help troubleshoot if your code is not working or it looks like your model's right and you've forgotten something and it's still not getting the right answer. Both of us are happy to help with that. And Vladimir, you did the homework in both packages, right?
Yes.
So he's ready to help you no matter whether it's R or Stata or even SAS if you want to. Or technically SPSS too. Like I'm not covering that, but you can use it for this stuff. SPSS doesn't have as ready estimate statement type things, so the linear combinations piece in their GLM package is a little bit clunkier. They have an option called test in mixed model packages that will work a little bit better, but then you don't get residual variance. So 6 of one, half dozen of the other. Anyway, last time we were talking about just starting with this model right here in our example. Does that sound about right? Maybe? So big picture, what we're trying to do here is review linear modeling principles in a familiar setting of regression before we extend those same principles into models for different kinds of outcomes. Like, I want to know that everybody is comfortable interpreting slopes, recognizing when slopes are conditional on other effects in the model for higher order interactions, and being able to, the word that is used for this is probe. I dislike that word, but probe interactions. I would say how to explain them would be maybe a more pragmatic way of putting it. I want everybody to be able to interpret interaction terms and recognize the implications of them for the other effects in the model. So we're going over this in detail. That way, when you see it in the context of predicting, say, a binary outcome or a count outcome later, it's not all brand new stuff at the same time. So the idea of an interaction goes along with a key vocabulary word that starts with an M. What word is that? Interactions test the idea of what? Moderation. Now, you might also be thinking of an M word that starts with mediation. You heard that M word? Those are not synonyms. They are not. It's easy to confuse the two, but they mean different things and they're tested in different ways. The idea of moderation is, does this predictor's slope depend on some other characteristic of the person? Do we have different slopes for different kinds of people? So in this model, for instance, I have added, we're predicting cognition still from age, grip strength, gender, and a 3-category dementia status variable to that main effects model, as I had called it, because these are all the main effects. So the terminology is switching once you have interaction terms. They're all slopes, but they are more specifically main effect slopes. Beta 6 here, this is my interaction term. So it's between age and grip strength. Note that it's the centered version of both of these, so we're staying internally consistent across what 0 means. This is answering 2 different questions at the same time. One of them is, does the effect of age depend on how strong you are? The other is, does the effect of strength depend on how old you are? Either of those interpretations is equally correct. One of them may be more interesting to you, but we can talk about it either way. Mediation, let's say that we had something like age as the predictor and grip strength as a mediator. That would be more like, okay, so being old makes you weaker, and the fact that you're weaker makes you do less well on this test. That's mediation, where the variable that's the mediator is thought to be like an intervening cause of an association between an X and a Y. So this is moderation, not mediation. Mediation is something we will get to at the end of this semester in a path modeling context, because that's the cleanest way to do it rather than having to rely on separate models. These 2 predictors are being treated as continuous. The fact that age has only a linear effect in this model and grip strength has only a linear effect in this model means that we only need one interaction term to describe their moderation. That will not be true, for instance, if I wanted to moderate dementia group with something else, I would need multiple interaction terms. That's the last model in this example. Okay. With me so far? Any questions before we dive back into looking at this stuff? I've got this model in Stata and I've got this model in R. So we can have an example of both since the output looks a little bit different. So first off, the stuff that shows up by default. C dot in front of, by the way, all of these predictors means they're being treated as continuous. You do not need to make interaction variables separately. You can make them on the fly as part of the model. So this term right here with the middle, depending on how old you are, this is either a hashtag or a pound sign. Solidly generation Z right here, that is a pound sign. Hashtag pound sign. See, that was a joke, right? Like I have a hashtag that's pound sign? No? I thought it was funny. Tough crowd. So all programs have a way to do this in general regression packages. It is a star in SAS, it is a star in SPSS, it is a pound sign in Stata, and it's going to be a colon in R. Stata gives me a traditional sums of squares table that describes the overall model, how strong of a prediction it is, and whether that's significant. So I've bolded the values that you would report as part of your homework, which would be in a standard results section otherwise. So the F-test for the model is right here. 36 is the test statistic that describes how well the 6 slopes work together to predict cognition. So the degrees of freedom here, this is numerator degrees of freedom as it is called for the F-test. It is the number of slopes that you have. Denominator degrees of freedom is right here. Do you remember how we would think about that? Yeah, how many slopes left over that I could have added? If I added 543 slopes, I would perfectly explain cognition. I've got a lot of room here. 549 is the total here. 550 is our sample size. The difference is the fixed intercept. It is always included. That's what the 1 is that makes it different. Just knowing that our model has a significant prediction doesn't tell us how good that prediction is. To answer how good is it, what do we look at?
R-squared.
Yeah, one of the R-squares. Whether it's real or adjusted, take your pick. I don't really care. I will ask you for the regular one because I know for sure that that will be the same across packages. So this is a proportion. I would say this as 29% of the overall variance in cognition was explained by my 6 slopes. That means that I've got quite a bit left over. This number right here also has special meaning. It's labeled as mean square residual or mean square error, but I would call it what? Residual variance, yeah. The amount of variability left over after introducing the effects of your 6 slopes. So this will be the first number that I ask you for in any model in your homework, residual variance. If you get this right, then you have the right contents of your model in terms of what you're predicting and what the predictors are. The next thing that I will ask you almost always is what the fixed intercept is, which is at the bottom of my screen here. I ask you what the fixed intercept is because that tells me if your predictors are centered correctly. The fixed intercept is the expected outcome when all the predictors are 0, so they have to have their zeros in the right spots. So according to this model, 29 is my predicted cognition outcome for what kind of person?
89-year-old.
85-year-old? Yeah, it's 84 in the class before. 9 pounds of grip strength, who's a man, without dementia. Yep. Do I need to add anything to that set of conditional statements because of my new interaction term or no? I would say in this case, the intercept is going to differ numerically as a function of the interaction being introduced, but it doesn't change who the reference person is because age 85 and grip 9 were already part of the story. So it's a different prediction, but it's the same reference point or type of person here. So then vocabulary that we introduced last time with respect to the kinds of slopes. Choices are bivariate marginal, unique marginal, or unique conditional. So in this model, because we have multiple predictors, that knocks out one of the choices already. Bivariate. This is, some would call this multivariate. I reserve that term for multiple outcomes. You might call it multivariable, but more than one predictor. So it's not bivariate. So each of these slopes is either unique marginal or unique conditional. The part unique means after controlling for the other predictors. Like what does age bring to the table uniquely that is not also contained in these other pieces of information about a person? So if they're all unique, then the distinction of marginal versus conditional is what? Say it louder, please. If it's part of an interaction. So the rule is a predictor slope becomes conditional on any other predictor that it interacts with. So if I look at the first two here, age and grip, because they are part of an interaction, these slopes are unique, but they are conditional. Another way to phrase that is a simple slope, although that's a terrible name and it should be complex slope. So I can't just say, for every year older you are, cognition goes down by 0.34. I can't say that. Well, 3.3, excuse me. I have to add something to the end of the sentence to make that correct. So for every year older you are, cognition is lower by 0.33, ... What's the end of my sentence?
For someone with a grip of 9?
For somebody with a grip of 9 specifically. Yep. Because that is the point at which this extra piece that also has age in it would zero out if grip is 9, and then the effective age would solely be due to this one slope. Otherwise, the effective age is a compound slope that has grip strength embedded inside it. Likewise, for every pound I can squeeze on the little thingy, cognition goes up by 0.62, ... Close. This is per pound, but it's conditional on the interacting variable. So for what kind of person is this the grip strength slope?
85 years old.
Yeah, 85. So that, because that's when the interaction term would drop out, as if that part is 0. Good. Now what about the rest of these? Beta 3, 4, and 5 for the effects of gender and dementia group. Are these marginal or are these conditional?
Marginal.
We got to vote for marginal? Anyone else want to vote? Couple votes? Zoomers, do you want to vote? Marginal or conditional for these 3 slopes right here? Oh, marginal. We got marginal in capital letters and marginal with a question mark. So some degree of uncertainty as to our answers. I once had a professor tell me when answering a question or writing a paper, it is better to be wrong than vague. I like that. Like, you take your, like, marginal. You're wrong? Okay, but you made a guess. The answer is marginal because these do not interact with anything else in the list here. So another way of saying it is that the gender difference favoring men, because this is a negative slope, it applies to the women. So men are higher by 3.5, women are lower by 3.5. That gender difference holds regardless of your age, regardless of your grip, regardless of your dementia status, because those potential interactions are not in my model. Likewise, these are the dementia group differences relative to none as the reference, regardless of your age, grip strength, and gender. Now the interaction term. What do I do with this number? That's the tricky part. There's only 4 kinds. An interaction term takes its constituent main effects and makes them more positive, less positive, more negative, or less negative. So if I start with age, that number right there, zoom in so we can all see a little bit. We said this is the age slope for somebody with grip 9, right? In somebody with medium level strength, age has a significantly negative effect. The older you are, the worse you do on this test. Given that the interaction term, hang on here, is positive, which pattern is this? It's taking the age slope and making it more positive, less positive, more negative, or less negative?
It's less negative.
Yep, we got a couple votes for less negative, and the Zoomers as well. Yep, this is a less negative. So more specifically, the age slope is minus 0.33 if grip is 9. For every additional pound of grip, that age slope becomes less negative by 0.12. For every additional pound of grip strength, the age slope becomes less negative. Note that the word cognition, the outcome, is not in my sentence. What happens is the interaction term changes the main effect slopes. The main effect slopes, in turn, change the outcome. It's like a trickle-down process of logic. Now, if I were writing this in a paper, I might describe this as less negative. Reviewer 3 would probably not be happy with that. Can you think of some other ways to describe it that might be a little bit easier to follow? But is this a stronger effect in stronger people, or is it a weaker effect? It's weaker. because this coefficient is getting closer to 0 as grip strength increases, and eventually would become positive if you followed it up far enough. So if grip makes the age slope weaker, then another way to say that might be age is less of a factor in strong people. Age matters less. Now, I'm not saying it doesn't matter, but it matters less is the pattern here. So we know that age matters specifically in grip 9. We don't know at what point this coefficient would stop mattering. But you know that as grip strength goes up, this number is going to keep getting closer and closer to 0, and eventually, somewhere, it's going to turn non-significant. And if you follow it, like it's a negative slope, eventually, it's going to turn positive if you keep going. So one of the things that we'll look at then is what would it be in somebody, say, who's stronger or weaker, and at what point does this stop mattering? At what point does it cross the threshold of significance to become 0 rather than negative? Okay, with me so far? Let's go the other way. Let's start with grip. So we'll make grip the focal predictor and age the moderator. So this grip strength slope says for every additional pound you squeeze, cognition goes up by 0.62 in 85-year-olds. In older people, what happens to the grip strength slope? Which of the 4 are we looking at here? More positive, less positive, more negative, less negative? More positive, stronger. Grip strength matters more in older people. The grip strength slope of 0.62 is significantly more positive or stronger by 0.12 per year of age. So this is still a per unit idea. It's per unit of the other variable. That's the key. It's always the other one that's the moderator. So grip matters more in older people. Another way to say that is grip matters less in younger people. If grip matters less in younger people, eventually it's going to stop mattering. So that we can find a spot on age where this positive coefficient would become less positive all the way down to 0 and non-significant. Same thing. The idea of trying to find the boundaries of where these slopes sort of turn on and turn off in a significant sense, that's called regions of significance. And you have a couple articles on your reading list that explain this in more detail, and I've got example code for how to get that information out of your stats packages. Not in Stata, unfortunately, but I built an Excel spreadsheet that does it, and our packages I've included in this as well. Okay. How are we doing? Feeling okay with this? Maybe? So what people would typically do then is make a picture to describe the interaction terms. And we got to make the predictions that make the picture. Other pieces of information here that I've requested that don't have to do with the interaction, but I want to be complete with respect to the analysis. The third group difference for dementia. So we did this one before. It's still beta 5 minus beta 4. So it was around the same size after controlling for the interaction. I have 2 examples of multivariate Wald tests that would test multiple slopes at the same time. The first one here is how you would ask, is there an omnibus main effect of dementia? Pooling the 2 slopes together into a 2-slope analysis. So the numerator degrees of freedom for that F would be 2 because that's the number of slopes being tested. The denominator degrees of freedom is still the 543. And that's the F value for it. So yes, that's lumping together these 2 effects to talk about them as a joint combination. And just to illustrate that we can do this for any combination, if I had a hypothesis that wanted to know what is the joint combination of age and grip strength, well, that takes 3 slopes, given the interaction term, to describe those. So I can do a test for that as well. You can lump together anything you want. Now, how to figure out what the slopes would be at other levels of the moderator besides the one that's given. So we did this last time in formative assessment number 1, question 3, but here's another instance of it. So the rule is 3-step process. Start with your model. So you can either write out an equation like this, or more simply, you can look at your code. Start with the model. What slope am I trying to estimate? The first one that I'm doing here is the slope of h. So I go into my model, I find all the terms that have h. Only those terms that have h. So I need the main effect of h, as it is called. I don't need the main effect of grip. I don't need the main effects of gender or dementia, and I do need the interaction. So just 2 terms involve age here. Okay, so I bring those down. There's the first one. There's the second. Now I factor age out and stick it at the end. And what's left in brackets are the ingredients by which I can compute what the age slope would be for anyone, according to my model. So I'll show you how to do this in both of the programs. First, this is Stata code. LinCom stands for linear combinations. So when you see the name of the predictor in these types of statements, what it is referring to is the value of the slope it is to get in the solution. The number that beta 1 becomes, that is what this word is referring to. So the times 1 here is not strictly necessary, but I have it for symmetry with the other programs. I need 1 beta 1 at a minimum to get an age slope, because that's where it starts off with. Then the question is, for whom do I want the age slope? I need to know the value of the moderator. At what value of grip strength do I want the age slope? Well, this one I have is at 6, because 3 is roughly 1 standard deviation. So this is a very common thing people will do, is compute simple slopes at a high, medium, low value of the moderator. So this would be low, medium, high right here. So I have -3 in here. And why is it -3 and not 6? If I want the age slope for grip strength 6, why am I typing -3? Because it's centered at 9. Yep. So 9 minus 3 is the 6 that I'm after. Don't forget that part. The middle one is age slope at grip 9. You note that I don't even need to write this one. This is literally what the simple slope of age means. That part would drop out if I multiply it by 0, so it's just here for pedagogical reasons. Likewise, if I want the age slope for grip equals 12, I put in a 3 here as the moderator. So I can request an age slope for any value of grip I want. I'm not cutting it up into groups or anything like that. I'm just requesting predictions. Stata has a built-in way to do this more efficiently using their margins command. dy dx means the derivative of the function with respect to age. So you put the variable you want the slope for here, and then you put the range of the moderator that you want in the parentheses here, where it's from by to, excuse me. So start at -3 in increments of 3 and go up to 3. So this one line of code does the exact same thing as these 3 lines before it. And I could do a lot more. Like if I did -5 in increments of 1 up to 5, that would get me 10 simple slopes in one fell swoop. Here they are. So the middle one is the one that we already have. Let me see if I can get, yeah. This is the age slope for somebody with grip of 9. That's what we already got out of our model. The other 2 are the new ones. So if I have grip strength equals 6, my age slope is 0.7, which is significantly negative. If I have grip strength equals 9, my age slope is smaller, less negative, but still significant. But if I have grip strength equals 12, then my age slope is non-significant and actually has turned positive. So does age matter? You can't answer that question with a yes or no. It depends. If you are relatively weak, -1 standard deviation up to the mean or weaker, then age matters. But at some point between 9 pounds of the moderator and 12 pounds of the moderator, it shuts off. We can figure out exactly when that is. We'll do that momentarily. Likewise, if I want to go the other way and focus on grip strength as the slope and age as the moderator, same process. Go into the model, find all the terms that have the grip strength slope that I want. In this case, it's the main effective grip and the interaction. Factor out the predictor the slope is for, and what's left in brackets are the ingredients. So at a minimum, I need a beta 2, and that's what the word grip means here. I'm referring to its beta in the solution. Now the values that are multiplying the interaction term are the values with respect to age as the moderator. So the -5 means I'd like a grip strength slope for an 80-year-old, please. The middle one, I'd like it for the 85-year-old, and the top one, I'd like it for the 90-year-old. So then the code, to simplify it, switches where age and grip are, because grip is now the slope and age is the moderator. And here are the 3 slopes that we end up with. So the first one is for an 80-year-old. If I'm 80, does my grip strength matter? No, it's pretty much 0. If I'm 85, does my grip strength matter? Yeah. If I'm 90, does it matter? Still matters. So somewhere between 80 and 85 is when this slope turns on, so to speak, becomes significantly positive. We can figure out exactly where that is. Stata anticipates that you'd like some pictures. So I asked for predicted outcomes for a range of low, medium, high grip strength, which is going to give me 9 points. I am conditioning on the other variables being 0 because they're not part of the interaction story. They would adjust the outcome up or down, but they wouldn't change the slope of the lines. And then I made some pictures. So now these plots show non-parallel lines. Coincidence or consequence? Consequence, yeah. So this is showing age as the predictor on the x-axis and different lines for different grip as the moderator. So the blue slope shows the strong negative effective age in a weak person, grip strength of 6. The red line is the slope given to us directly by the model for grip strength of 9. And the green slope is for grip strength equals 12. So somewhere between the red line and the blue line is where it becomes, is it that one? Hang on, I think I forgot. Let me go back up to the data here before I say that incorrectly. These two, somewhere between 6 and 12. Yep. Somewhere between red and green is where it shuts off. I can go the other way. This is showing grip as the slope. Now it's positive. And the red line is what's given to us by the model directly. And in this case, somewhere between blue and red is where the slope shuts off. Okay, how are we doing? So if you wanted to figure out exactly where these slopes shut off, the so-called regions of significance, there is a very complicated formula. I programmed it into Excel. There are also people's like Shiny apps and stuff that you can find online that have done this. The pieces of information that you need to feed into either my Excel formulas or the Shiny apps include something extra that you don't normally ask for in your output. So I'll show you how to get it out of Stata. It is the command SStat, meaning like extra stuff. VCE stands for asymptotic covariance matrix of the fixed effects. Now what the hell is that, you might be asking? Well, on the diagonal of this matrix are the standard errors for each of my slopes squared. This is a term that I don't normally use, but in case you've heard it before, the idea of sampling variance, like how much your slope would wiggle around across repeated samples of the same kind. It's not going to be the same number each time. This is the variance of that wiggle. The standard error is like the standard deviation of the sampling distribution. So normally we get the square root of these things as the standard errors. These are the squared versions that need to go into the formula. And I've also bolded the pieces of information required that are part of the off diagonal here. These are covariances, because what a given fixed slope is for one variable is going to be related to what it ends up being for another. Like if one is a little higher this time, this one might need to be a little bit lower to compensate. So we need the covariances among the standard errors for these terms. So these 5 pieces of information you would need to get to plug into the Shiny app or the Excel sheet. Or you can use R and find a package that does it for you like I did. So this is where I do like R packages to simplify calculations that would otherwise be painful and tedious. They're very good for things like that. Okay. Would you like to see the same thing in R? Those of you who are learning R. Question first?
So I'm just wondering if that covariance is the same, like the covariance of the arrow is the same as the covariance of this 2 vector.
I'm not sure I follow your question. Keep talking, please.
They have a standard arrow, a standard.
Every fixed slope has a standard error that goes with it that you can either try to find empirically or you can rely on formulas to spit it out for you. And we're relying on formulas here.
You said that correlation, that's not the covariance is the covariance of the standard arrow.
Yes, it is the covariance of the standard errors.
Is that same thing as the covariance between that like age 85 and
No, this is not the covariance between the variables. It is the covariance between their slopes, essentially. It's a different concept. We don't normally, you could ask for this matrix out of any package, but we don't normally care about it. I'm just pointing it out because if you try to compute regions of significance, it will ask you for the standard errors in a squared metric usually, and because these values can get really small, you want them to be as precise as possible. So like taking the value on your output and squaring it will not be as precise as getting to what it is stored internally. But these covariances are the extra pieces that don't normally show up. Yep. All right. R code then. So I have my call to LM. My formula now includes the interaction term at the end, and a colon forms the interaction term on the fly in R syntax, at least for 2 different variables. Here are my model coefficients. They are exactly the same as what we just went through. The only difference is the order in which they're listed. Intercept comes first in the linear model's output, as it should, damn it. It's the first thing in the equation. Why doesn't the first thing in the table? So yes, so the numbers otherwise all agree. The F test for the model and the R square are buried in this little paragraph here. The residual variance is obtainable separately using a function ANOVA. So I've truncated the table just to that number that we want. So this is my mean square error or mean square residual variance thingy. We went through the interactions. Do you want to go through these coefficients again, or are you feeling okay with these? Feeling thumbs up, thumbs sideways, thumbs down. Feeling okay means thumbs up. Okay, the roomers are voting up. Zoomers. We have a selective sample of people who are willing to admit when they understand something or not, admittedly. But of those people, everyone is giving me thumbs ups. Well, you know what? If you need to hear it again, you know what you can do? Go replay the recording. Yeah, now I'm like, did I start it? Yes, I did. Yes, I promise you, by the way, if I ever forget to hit record, I will re-give this lecture in my basement the next day. I promise you I will do that. But I can't even tell you how many stats classes and workshops that I sat through in my life where I thought, you know, if she would have just said that one more time, I would have had it. You can listen as many times as it takes. And you can review the transcript if I'm talking too fast, which is another nice boon of technology. Okay, so thumbs up saying we're okay with this. Let's focus on the code to get the extra pieces of information, because this is something I shall ask you to do in your first homework. So the additional pieces of information, we're using GLHT predominantly. The first thing I'm asking for is the model implied difference between the non-reference dementia groups, so the beta 5 minus beta 4. Do you remember what the order of these numbers means? How you figure out what's what? Say it again. These are the betas. In the order in which they are shown on your output. Okay, so this is where I have learned this the hard way when I always do my analyses for these handouts in multiple packages to make sure that I've got the same answer across, and that checks my code as well. Let's go up to the R code here, okay. Now, my inclination, potentially in writing this model with the interaction term, might be to stick it behind the two variables right here that it interacts. So I'd have like age, grip, age by grip, and then the other stuff. If I do that, do you know what R does to me? It's like, nope, I'm putting it at the end. Too bad. So if you are trying these GLHT statements and it's not working, that's the first thing I check, is make sure that your listed order that you're thinking of them is indeed the same order that it's thinking of them. Let me move this back before I screw that up. So the place that corresponds to each of these zeros or ones is the beta that this is the multiplier for. Okay. So in the other packages like Stata, you list the predictor variable, and that is referring to its beta. It is implied because this is the first slot. You know that we're talking about doing something to beta 0. The second slot is for beta 1, and so forth. So this is saying ignore beta 0, beta 1, beta 2, and beta 3. Give me beta 5 minus beta 4. That's what it's doing. So minus signs are to do subtraction. If this were not a minus sign, then I'd be asking them to be added together instead. So I'm making one new term that is either an addition or subtraction of existing model fixed effects. So there's my minus 10, which is the difference between the two non-reference dementia groups. Here is a different use of the same function, where I am being more explicit that I want to test two slopes jointly. So this is the omnibus main effect of dementia group. It's a joint F-test for whether these both slopes are both 0. Yes?
Why is it where it says print, like why is it degrees of freedom number equals 2?
So, good question. This way of doing it, the comma separates out your numerator degrees of freedom. So I'm not saying add these two slopes together. I'm saying set both of them equal to 0 and tell me how much worse my model is. So the F-test numerator degrees of freedom is the number of slopes in the test. That's why the one for the model would be 6, because that's how many slopes are all together. If I just want to know about these two, then that would be 2. The other example that I have where it's age and grip and their interaction, because I have 3 slopes, then the F has a 3. So this is another way that you can check that R is doing what you want it to. You know how many slopes you wanted. See that the number matches. The numerator degrees of freedom changes as a function of the number of slopes. The denominator degrees of freedom, DF2 as it is labeled here, does not. That's a function of how complex your model is and how many people you have to start with, n minus k. All right, simple slope time. So if I want the age slope, grab all the terms that have age, factor it out. Here's my ingredients. The first 3 lines in this statement are giving me those. So the 1 is, I'd like 1 beta 1, please. And I'd like you to add to it -3 times beta 6. So this is the main effective age in the second slot here, the interaction term in the last slot. So the value of the moderator you want the slope for goes in the interaction spot. The slope you want in the first place gets turned on by putting a 1 in its spot. So that's why the last 3 rows have a 1 in the third spot because we're talking about beta 2 as the third term. So this is doing the exact same thing as the Stata code, and this is why in the Stata code, by the way, and in the corresponding SAS code, I use times 1 here, because I'm trying to, like, that you got to turn it on. Like the 1, that's what it does, even though it looks silly when you write it that way. You need it when you start writing things out this way. Okay. With me so far? Maybe? Any that you want to hear again? Or anything I can say that might make it a little bit better?
What is the test adjusted for? Test is adjusted.
Tested this part? By default, it tries to do some kind of multiple comparisons testing thingy on this, where it chops your p-value down. I don't see the point of that in this context, so I'd shut it off. So let's be real. This is tedious, right? We can all agree on that. Like, once you know how to do this, it's like, ugh. You should see some of the code that I have in, like, the advanced longitudinal class, where there's 13 slots for my fixed effects and you're turning each of them on and off. Very tedious. It's slightly less tedious if you throw yourself a bone and put a label in here to help you know what is what. So when you're doing homework, I would take the time to actually change these words. Like, in your output, you don't have to change them, but this will not help you figure out what you're looking at if you don't. I've also seen people do things like, you know, this is the answer to question 23. That way, like, you can look back at it more easily when you're looking at your output. Because I will ask you, like, what the estimate is and what the standard error is, and later you have to look at the p-value to make a decision as to how you would talk about it. The green doesn't matter, though, right? That is correct. The green is just the label that shows up in this first column here. So you can write whatever you want. So you could, like, you know, put it in here like, you know, stupid Lisa homework. Right? And that's what it will say on your output when you see it later. Now, that won't help you figure out which stupid question it is, but this is, you can write yourself anything that you want. And you'll note that this one here and this one here are unnecessary. If you look at their contents, there's only one 1 in one spot in each of these rows. These are not linear combinations. These are the simple slopes that will show up on your output by default. The reason that I write these this way is both for pedagogical purposes, so you can see the pattern, but also to do myself a favor when I'm looking at my output like 2 years from now, to have it all in one table neatly labeled. Much easier than trying to recreate, what did I do, what does the centering mean, what does this mean, like, after the fact. So labeling things in a way that allows you to track them down later will be helpful to you. But this is tedious and error prone, because it's real easy to put a 0 or a 1 in the wrong spot. So that's why once you get good at it, you can start to rely on other people's time-saving routines, such as this. So I found a package called RegHelper. Presumably stands for regression. There's a bunch of different packages that do this, but this is the one that I found. So in this, you can ask what values of the moderators you want. And so I asked for 2 sets. So the results of this one line of code right here is the same as what I did up here with the 6. It's the same. It's a little bit harder to figure out what it means, though, if all you have is like this. You have to know that this is the slope of test, as it is labeled here. These are age slopes at these values of the moderators in the first 3 lines. It's backwards, grip slopes at the values of the age moderator in the last 3 lines. Okay. Questions or comments on that? Regions of significance, then. There is a package called interactions that I found that does this. The function name is Johnson Neiman, who are the originators of this procedure. I want to say like 1934 or some shit like that. Like, this is really, really old. It wasn't until the 90s and the early 2000s, I think, that people figured out how to hack this previous procedure for this current purpose. So the articles that I give you on this topic go into the history of this a little bit more. This is another routine that calculates regions of significance. So the idea then is, at what point, for instance, does my age slope turn on and off? At what point of grip? And at what point of age does my grip strength slope turn on and off? So in this command, here's the first one where the predictor is age and the moderator is grip. I'd like 3 significant digits. And there's an option to make a picture, but when I did, it crashed my entire computer. It just caused R to hang and I couldn't do anything. So I don't know what happened, but I just turned the plots off. Probably because I don't have some dependency package installed correctly or something like that. But. So what it came back with is the text right here that I have augmented with the bold. So it gives me the interval of 9.6 up to 18. This is the uncentered metric. So when grip 9 is outside this interval, the slope of age is significant, but it tells me what the values are. So this is the values of grip strength at which the age slope switches from significantly, in this case, it would be, get the slopes again here. So at, the first one is 9.6. 9.6 is where this age slope switches to be non-significantly negative. And if I follow it up far enough, it becomes significantly positive at a grip strength of 18. So then the question is, what is the range of this predictor in your sample? Well, most of the people in the sample are going to be on the low end. So for most of the people, there's a significantly negative age slope. So this is the version that I wrote based on what the output said. The age slope will be significantly negative below grip of 9.6. It will be non-significant between grip of 9 and 18, and it will be significantly positive after 18. So I feel like for quantitative moderators, this is a much more useful thing than picking plus or minus 1 standard deviation as arbitrary points to find specific slopes. These are just predictions, but I feel like they're more useful because then you can compare this interval to the distribution of grip strength in your sample and talk about, okay, for most of my sample, this effect is negative. For these people in the sample, it will be expected to be non-significant and so forth. Going the other way, for age as the moderator and the slope of grip strength, the uncentered age interval is this, the centered interval is this. So grip strength will be significantly negative below age 70, non-significant from 70 to 82, and significantly positive after 82. So you can go either way on the moderators there. Okay. I'm not going to make you do regions of significance, but I did want to show it to you because I think it's very useful. Questions or comments? Then in that case, last but not least, points, so that we can make pictures in R. I'm using a package called Prediction. So it works a lot like the margins package in Stata does, where I feed it in the output from my model as the object. I tell it what I want to hold constant. Hang on, I need to make that blue. There. And I tell it the range of the predictors that I want. So start at -5, up to 5 in increments of 5. Start at -3, up to 3 in increments of 3. So I get 9 points. This is the output that I get. So then to make this into a data frame so I can plot it, I take this object, saved out of the summary, convert it to a data frame. I create new columns for grip that is uncentered again, so I add the 9 back and the 85 back to H, and then I can throw it in the plot, and this is the code in base R plot to do each of these pictures, and there they are. And yes, I was super proud of myself for getting a plot to work. And I don't want to hear about how ggplot would have done it. I don't want to hear it. I will point out, though, that I had to write like an entire page of code to get these pictures, whereas in Stata, it was like, hey, you want a picture? I can do that. This. That's it. So, Stata wins on this one. There's no ready way to do it in SAS either, though, unfortunately. So yes, when you're giving a presentation, when you're writing a manuscript, when you're giving a poster, any of that, do not put up a table of coefficients. Make a picture. Usually the x-axis would be the predictor that you care about, and the moderator would be different lines. But either picture actually tells you about the interaction. So the different slopes of age is one way to look at it. The other way to look at it is the different distances vertically. So what's the word I want? I'm out of words. The spread, let's go with that, across grip strength is bigger in 90-year-olds than it is in 80-year-olds. So in that regard, this picture still describes how the effective grip is moderated by age. Likewise, in this picture, it's focusing on grip as the slope, but you can say that there's a bigger spread as a function of age in weak people than in strong people. There. Not going to the next model yet, just sticking with my pictures. I don't know why the legend line looks black and not blue, though. Do you know how I would fix that in PowerPoint? I would make a tiny little blue line and overlay it. Be like, there, fixed. You can always go low tech if high tech isn't working for you. Practically speaking, although the plots are fine in R or Stata, do you know what I do almost all the time if I can? I do it in Excel. Do you know why? Because then I can give it to my collaborators who didn't run the analyses, and they can fuss with it all they want. In Excel, they can change the names of the labels, they can change the names of the axes, they can make it green instead of purple, whatever they want to do. Otherwise, they'd be like, can you change this in R? Can you change this in R? Can you change this in R? So Excel has some purposes for that. So when working with collaborators who aren't willing to invest in this level of coding, there are some ways you can save yourself some time. All right. You ready for a little more complexity? Maybe just a little bit today and then like next week. So this interaction term that we just looked at, for instance, this type of model that we had, the reason that it only takes one slope to make an interaction is because each of the main effect predictors only needed one slope to describe its effect. But that will not always be true. So here's an example of what it would look like, for instance, to have an interaction between group as a categorical predictor with 4 levels, 4 categories, and age as a quantitative predictor. This is slide 24 of lecture 1. So previously, we had looked at a dummy coding scheme in which control is the reference, and then D1 gives me the difference of how treatment 1 differs from control, D2 gives me treatment 2 versus control, and D3 gives me treatment 3 versus control. So because group takes 3 slopes to describe its main effect, if you want to see if any other predictor slope varies by group, how many slopes do you need? And don't say 1. If I want to ask, does whatever vary by group, How many slopes do I need? For each new whatever. If it takes 3 slopes to fully differentiate the 4 possible groups, and I want to know, say, if, for example, the effective age differs by group, how many interaction slopes does it take?
3.
You're voting 3? Is that what you said?
Yeah.
Okay, I've got another vote for 3 in the chat. I've got a vote for 2. Got a vote for 4. Somewhere between 2 and 4 is correct. I'll tell you that. We'll narrow it down. I said don't say 1. The answer is 3. Because it takes 3 slopes to differentiate 4 groups. It will take another 3 interaction slopes to differentiate the effective age across the 4 groups. Like this. So conceptually, the way that I would think about this model is age, group, and age by group. Conceptually, those are 3 ideas. Mathematically, group is beta 1, beta 2, and beta 3. Age is beta 4. And group by age as an interaction term is 5, 6, and 7. Takes 3. The same logic in terms of what these tell you directly versus what is available indirectly through linear combinations also holds. In general, in this type of coding scheme, the model is going to directly tell you about anything relative to the reference group. Each of these differences is relative to control. For the same reason, this beta 4 slope of age is going to be for the control group specifically, because that's when all my new interaction terms would zero out. So I would have to ask for several different pieces here to make this work. Conceptually, I have a request to repeat that. Conceptually, yes. So the research question basically that would go with this is, does group matter? Does age matter? Does age matter more in some groups than others? Group, age, group by age as 3 concepts. But group is D1, D2, and D3. Those 3 slopes, beta 1, beta 2, and beta 3 for those variables. Age is just 1 because it's a linear effective age. Group by age as one idea. Does the effective age depend on what group you're in? That's beta 5, 6, and 7. So if I wanted to test group by age, this is an example of the lumping process. Multivariate wall test. I would need a joint F-test for beta 5, 6, and 7. I would also potentially want to talk about group differences, but I can't just talk about group differences in this model without conditioning on age. So beta 1, 2, and 3, because of these 3 interaction terms, they are specific to an 85-year-old. Likewise, beta 4 is specific to the control group as the moderator because that's when these things go out. To get the effective age for the alternative groups or to get group differences at other ages, we would have to go deeper and ask for them as linear combinations. And by the way, your homework, last model, is like this. 4 groups, a continuous interacting variable. So yeah, this is not just hypothetical. This story is hypothetical. I'll show you what it looks like in code for a slightly simpler example, but then I'll be looking for you to extend that example into the story problem. So here's my model, and here is the algebra that it would take to figure out how to get model implied differences and slopes. If I start with the effective age. So if I want to talk about the age slope, the model is only going to give me the age slope in the control group. What if I want to know if age still matters if I'm being treated? That's a question. So the rules are the same. Go into the equation, find all the terms that have the slope in question and bring them down. In this case, it's the slope of age. So I know at a minimum I need beta 4, and the other interactions involving age turn on or off as a function of these dummy codes sitting out front. So if I want the effective age in the control group, that's the one I already have because that's when these 3 are 0. It boils down to just beta 4. If I want the effective age in the treatment group, then I start with beta 4. This tells me what the slope of age is in control. Then beta 5 kicks in and says, hey, what is the slope difference in the treatment group? That's what beta 5 tells me. If I add these two together, I get to the full age slope in treatment 1. So the interaction terms are differences in slopes. Slope differences or differences of differences is another way I've heard it phrased. So beta 5 tells me how different the age slope is in the treatment 1 group. If I add that to what it is in the control, then I get to what it is in the 1 group. And the same thing for these 2 other treatment groups. If I want group differences, conditional on age, same logic, different side of the coin. I need, at a minimum, my beta 1, 2, and 3 group differences, and then the question is, do they turn up or down as a function of age? So beta 1, beta 2, and beta 3, these little equations show it, I think, a little more directly. These have to be specific to age 85 because that's the only age at which the rest of this drops out. Otherwise, if I wanted it for, let's say, a 90-year-old, then I would fill in 5 here, and it would be the interaction term times 5. The interaction term describes what happens to beta 1 per year of age. And here are the model implied differences between the non-reference groups. If you can get these differences, then you can subtract and get the 2. I don't think I asked you to do this, though. I'm not that mean, at least not yet. The point of the story is that the information is in there because this model has enough content to tell me what the group difference would be in any age and what the age slope would be in any group. I'm only going to get certain realizations of that, though, by default in the output based on how I phrase it. So this is the logic by which you can find it. And then these are the ingredients of the programming statements that you can ask for. Yeah. 3-way interactions, not today. I'm not that mean. If you don't want to do algebra, and you don't want to write extra code, can you think of a trick that you can use to avoid this problem? What if I want to know group differences specifically for an 80-year-old? And I don't want to write any extra code.
An 80-year-old?
For an 80-year-old, I said. What would you do?
Change the centering.
Change the centering. Yep. If you change the centering of age to make the 0 group 80, now the main effects of group here, beta 1, 2, and 3, are going to be for an 80-year-old because that's where it's 0. I could do the opposite, like if I wanted to know like all about treatment 1, I could change my dummy coding scheme so that they're the 0, and then everything in the model is relative to treatment 1 as a reference. That's how I initially learned how to do this stuff. That's not wrong. If you'd like to take that approach in your homework, Godspeed. It does get confusing though, because you end up with the same model like 4 times, and you need like different parts of it to get the whole story. So it can be a little more work to reconfigure it after the fact, but that is an alternative. And sometimes if I have a really complicated model, that is what I do, because it's just easier sometimes. But you'll have all the tools you need to figure out what is going to work best for you. Question?
If you do that, then would you still be including the control group, or would
So if you changed it so that treatment 1 were the reference, then the second column here would be zeroed out, and you'd have to recode this first one to have a 1 here instead. And then treatment 1 would be like the reference, and it would say, how does control differ from treatment 1? How does 2 differ from 1? How does 3 differ from 1? And in that case, the main effective age would be for treatment 1 specifically, and the rest of these would rearrange themselves with the same pattern of zeros and ones, turning things on and off. Yep. All right. So next time then, we probably will be able to finish this unit, I would say. We will look at an interaction in our story problem between dementia group and gender, because that's only 3 groups instead of 4. So it's not quite as overwhelming, but this is how it would be extended to 4 instead of 3, just an extra set of demicodes. So that, let me get the thing here. That's where we're headed here, is adding in, keeping our age by group interaction, but adding in 2 new interaction terms that allow the effect of dementia group to vary by gender. At the end of the day, there's only 6 different cell means, as they call it. This is a NOVA language. Does Ariel use that term? Cell means or marginal means? Yeah? Okay, good. So I can get the gender difference in this group, the gender difference in this group, the gender difference in this group, and I can get how the gender difference differs between this group and that group as the interaction. Or I could go this way. I could talk about how dementia differs across men, how dementia differs across women, and how dementia differs differently between men and women. That's where we get into the differences in differences language here. So there's a bunch of possible pairwise comparisons. The model's only going to give you some of them, but we can get the others. So I'll show you how to do that next time. All right, any questions before we call it a week? Not just a day, a week. Not right now?
I have a question about the testing of significance of group of slopes.
Mm-hmm.
You said we can do that with multivariate word test,
Yes.
but just like it will only tell us if they are significant, we can't know how much significance they have. What I mean is how much they contribute to the proportion of the variance they are explaining.
So
without fitting those specific slopes separately in another model.
So the question was, we can get an F-test that lumps together multiple slopes. So for instance, let me go back to an example of that. So like we can lump together these 3 slopes if we want to have a significance test of that. So then if you want an effect size that goes with it, like how much of the R-square are these 3 slopes responsible for, what you want is a semi-partial eta square. That is what that means. Semi-partial eta square is the amount of the R-square that is due to the thing in question. How easily that number is available to you differs by package. In SAS, it is a contrast statement, and the effect sizes in the F show up without you having to do anything else. I looked for this in R, and I could not find a way to do it other than to do what you just said, which is take them out of the model, see what the R-square becomes, and then see what the difference in R-square is with and without them, and that's your semi-partial eta square. So I think you can always do that. You can always take them out, see how much R-square went down, and that's your answer. How to get it without having to fit multiple models is easier in some packages than others. Stata is the same way. Yep. What we're going to do in this class for these sorts of joint hypothesis tests was we're going to switch to likelihood ratio tests in this class because the multivariate wall test gives different answers in R than in Stata. Of course it does. So, all right, 316, overboard. Thanks for being here. Let me know if you need anything. Have great weekends, and let me know if you need help with your homework. Happy Thursday. Happy Groundhog Day.